All right, class. So I want to welcome you to this particular lecture from Chester Sokolowski. Chester is a PhD candidate here at FSU. He works for Dr. Kim. He's been at our university kind of working alongside our group and working with Dr. Kim for a little while, and he's highly interested in applied outcomes of resistance training and nutrition. You can also see a lot of him on various social outlets that I'm sure he'll mention at the very end of this for ways to find more of the cool things he's working on. So, all right, Chester, let's have you take it from here. Thanks so much.
Okay. Thank you for giving me this opportunity to present. I'm not sure if Dr. Ormsby clued you in anything about me. My personality is just kind of a little bit extra, like walk at Chipotle. Therefore, we're going to do some seriously great work, but we're not exactly going to take ourselves too seriously when we do that work. But anyways, let's jump in. Everybody can read research, but not everybody can find the applicable takeaways. So here's the outline. You must read more than just the abstract, particularly when we talk about these big landmark findings, some of the protein findings, big influential papers in performance and physique findings. So you got to really dig deep into the materials. Next, you must be critical about what you read. You always respect the research because research is extremely hard to do, but a healthy skepticism will serve you well. Next, be aware of potential bias when reading the paper. So researchers are people. Just because you throw on this white lab coat doesn't all of a sudden drown out your pre-existing beliefs and your pre-existing bias. And their pre-existing bias can influence the research. Lastly, you must factor in physiology. So all those little nitty-gritty details that you're learning in class, they can really help connect the dots and make sense of the conclusions. So first of all, lesson one, the abstract is not enough. I'm sure you guys are familiar with this paper, a systemic review, meta-analysis, and meta-regression of the effect of protein supplementation on resistance training induced gains in muscle mass and strength in healthy adults. This paper is where we get our protein recommendations from, the 1 gram per pound, the 2.2 grams per kilogram. They're derived from this paper. Before we jump in, let's just kind of look at the authors. We have Brad Schoenfeld. He's one of the most well-known, well-respected authors in physique and performance nutrition. I mean, if you go on his Instagram, he's got like 250,000 followers. If you go on his PubMed, he's got like 250,000 papers. So he's at the top of the game. He really knows what he's doing in this regard. Next, we have Menno Henselman, also a great researcher, very well respected, runs a great physique website. Eric Helms contributes to a research website. He's also made some fantastic contributions to the bodybuilding game. So this protein area and this muscle mass area, this is really his niche, it's his sandbox. Alan Aragon, he's made multiple very influential contributions, also has a great research review website. James Krieger research review website in its own right. He's made some great publications. And then Stu Phillips. Stu Phillips is essentially an encyclopedia in human form. I mean, the guy really knows everything there is to know about protein supplementation. And there are some people who I didn't highlight. They're also very fantastic, very great researchers. I'm just not as familiar with them on, kind of the social media platforms. But if you look at this, if you look at these authors, this is the top of the game. It's the cream of the crop. These guys really know what they're doing. So it would just be crazy to question the conclusion that they've made. But I'm essentially going to question the conclusion that they've made. So here's what we got. Here is the objective. Let's start here in this top left. I don't know if you guys can see my mouse. Hopefully it's clear. If not, we're starting top left. We performed a systemic review, meta-analysis, and meta-regression to determine if dietary protein supplementation augments resistance training-induced gains in muscle mass and strength. Let's jump down to the eligible criteria. Only randomized control trials with resistance training of greater or equal to 6 weeks in duration and dietary protein supplementation were featured. So we're talking about the greatest guys to do this research. We're talking about randomized control trials. That's the gold standard. Where we really have all the criteria we need to make a great conclusion. And they also, let's look at the results. They looked at 49 studies with 1,863 participants. So this is a huge data collection that they did. And they concluded, let's jump to this bottom sentence right here. Protein supplementation beyond total protein intakes of 1.62 grams per kilogram per day resulted in no further resistance training induced gains in fat-free mass. So this means if you eat more protein, greater than 1.6 grams per kilograms per day, you're not going to grow any more muscle if you're performing resistance training. A greater protein intake is not going to further contribute to resistance training induced gains. However, researchers don't like to be over specific. We like little ranges to play in, so they used a confidence interval, and the confidence interval capped at 2.2 grams per kilogram per day of protein intake. And this is where we get sort of our maximum intake for lifters of 2.2 grams per kilogram protein intake, or gram per pound. First of all, I want to kind of jump off Zoom. I'm curious if you guys had any questions when you read the paper. If anyone saw anything that jumped out at them, they want to chime in? Nope. Okay. So it was a well done paper. I mean, it was a great meta-analysis, a great review. But if you go towards not just the paper, but if you go online, you start playing around and clicking some links, you could see the supplemental data. So this is what we have. We have the supplemental data. We have the 49 studies. We have the 1,863 participants. And we're going to dive into that to see where this conclusion comes from. What is the data that this conclusion is based off of? Let's look at the frequency, first of all. Days per week of training. Let's start at the top. Hopefully you guys can see my mouse. 3, question mark, 5, 3, 3, 3, 3, 3. Okay, I see a lot of 2s and I see a lot of 3s. I see some question marks too. That's a little concerning. But I see a lot of 2s and a lot of 3s. Now think about how many times a dedicated, experienced person would lift if they're performing resistance training. I'm sure it's more than 2 or 3 times per week. Next, let's look at the volume. Let's look at sets and reps. So I see 3 to 4. I see 4 to 15 rep range. That's a good rep range, but I only see 3 to 4 sets per major muscle group. I see another question mark. I see 3 sets per major muscle group. 3 sets, 2 to 5. So we're talking about relatively low volume. I see a lot of 3s and I see a lot of 4s. If we go down, you could see some 2s and some 2s and even a 1. And then a lot more 2. So just on average, it's about 3 to 4 sets per major muscle group. In the rep range, I mean, we have some good, we got some 4 to 15s, we got some 5 to 15s, but then we see a lot of limited rep ranges as well. 3 times 8, 3 times 8, 3 times 10, 3 times 10, 3 times 8. Can you imagine doing 3 times 8 for 16 weeks? 4 months of 3 times 8, you'd probably get sick of resistance training. There's really only one study that had the applicable volume that we train at. It's 6 to 12 sets per major muscle group. And they also used a great rep range of 6 to 15 reps. That's a good range to stimulate hypertrophy. However, this one study that used appropriate volume when they were training, they just weren't training a lot. The average frequency is only 3 days per week. So in general, you could say that this is relatively low volume. Now let's look at the training status of the people. So their UT is untrained, T is trained. So UT, this is untrained, trained. Okay, maybe they're trained. Well, there's a lot of UTs, trained. So there's a lot of UTs in here. There's a lot of untrained participants. Okay, so I want you to think about the first time you've ever squatted. Could you stimulate muscle growth to the best of your ability? Could you train as hard as you can to trigger the most amount of muscle growth the first time you ever squatted? Likely not. Likely you don't want to rest the bar on the little pointy bone in the back of your neck, and you're not really concerned about how much muscle growth you're potentially going to stimulate. So this has limited applicability. You guys have people who don't necessarily yet know what they're capable of. They don't know how to push themselves. And let's think about the volume now. 3 to 4 sets, they're really not given a chance to really familiarize themselves with their body and push themselves too much. So in general, you don't have a lot of high quality volume in this, at least in page 1 of the data. Let's look at page 2. We see the frequency, it's a lot of the same thing. We got some 5s, we got some 4, and then a lot of 3s, a 2 or 3, a couple 2 or 3s. Not really sure what that is. Maybe they're trying to auto regulate, but 2 or 3, that's a little, question marks get raised. The volume for this page is seemingly a little lower. There's 2 to 4, there's a lot of 3s, there's more lower numbers. You even see some 1 or 2s. Let's think about the maximum protein intake you can handle, and you're only doing 1 set. If you're doing 1 set, that's not necessarily resistance training, it's like an extended warm-up. So 1 or 2 sets really is not going to create a demand for more protein. And then if we look here, it's essentially all untrained participants. So 75% of participants are untrained, yet this conclusion applies to all lifters. It's like, it's a bit of a head scratcher. Now that's all we're going to say about untrained participants now. We're just going to touch on untrained participants now. We'll go to third base with them later in the presentation. Anyways, let's look at the frequency that does apply to lifters. So, 5 days per week, 5 days per week. We see that there's 3 studies with a resistance training of 5 days per week. But we have 4 studies with question marks as the protocol. Let's go to page 2. We have 1 study with a resistance training of 5 days per week. I see no 6 days a week. I see no 7 days a week. We're capping at 5. Then here we have 2 question marks. So somebody check my math. I'm from an SCC school. We're known for our speed, not our arithmetic. But I saw 4 studies with a resistance training frequency of 5 times per week, and 6 studies with question marks as part or all of the resistance training program. You have more question marks than training frequencies that mimic what dedicated lifters do. There are more questions than data derived from the population this conclusion is generalized to. That's a red flag. Next, we need to consider the research protocols. Do these resemble what you do in the gym? And I think the answer is no. So we talked about kind of 3 to 4 sets per major muscle group. The major muscle groups you're going to hit are your chest, your back, your shoulders, your quads, your hammies, your biceps, and your triceps. And with this, you're likely going to get a machine chest press or maybe a barbell bench press, depending on equipment, but a flat chest press variant more than likely. Back, you're going to get a row variant, a dumbbell row, a machine row, something like that. Shoulders, you're pretty much always going to get a shoulder press, and then maybe a lateral raise. Quads and hamstrings, you're going to get a knee extension, a leg curl. Likely you're going to get leg press. You might get squats. We're starting to trend more towards squats. Biceps, this is a preacher curl machine. Triceps, a tricep extension machine, maybe a dip machine. So in general, there's a limited exercise selection. There's sort of limited equipment. And then additionally, we have a number of muscles that really don't get a lot of stimulus. The calves, the glutes, the back, the traps, the obliques, the abs, the forearms, lateral delts, the rear delts. These are relatively either not stimulated or significantly understimulated. So let's look at the calves and the glutes. These are 2 muscles that encompass a huge volume of your lower body that really don't get a lot of stimulus. I mean, I've never seen a resistance training protocol really do calves like we do calves. Calf raises are really, really rarely included. And then glutes, the glute training protocols are nothing like what's done in the gym. I mean, you're not going to see any wagons coming out of research. The glutes are significantly understimulated. And next we have the back. There's no way that you can sufficiently overload your back if you're just doing rows. Maybe you'll get an overhead pull variant, but still there's, different exercises that you can do to stimulate more portions of the back. The traps, they really don't get a lot of love. The core, there's really ever any direct ab work. And then the forearms, the lateral delts, the rear delts. So if we just kind of take a step back and look at this, is growth stimulated to demand more protein? I mean, we see maybe a large portion of your legs, a really good portion of your torso right here, and then a huge chunk of accessory muscles. I see like 30, 40% of the body that's really not really trained at all. And then the muscles that are trained, are they given sufficient volume? I mean, are they given enough to grow if you're doing kind of 3 to 4 sets per major muscle group and the exercise selection is rather limited? So they don't really do what we do in the gym, the multiple angles, the variation of intensities, reps and sets, and manipulation of rest intervals, drop sets, auto regulation, variation. Everything that we know can facilitate growth really isn't there. Now, granted, it happens for a reason. You need to standardize the protocol between participants. So you're not going to see a lot of drop sets or auto regulations because that means participants would do different things, and that's not exactly ideal. Secondly, other labs need to replicate the protocol. So you don't see too much variation, too many equipment changes, multiple angles, intensities, reps, sets, manipulation of rest intervals. You don't see that because it's just harder to replicate that. But the big thing, this last word, variation, the variety. Variety is, the spice of life. That's a common quote. But variety is also the spice of gains. You need to enjoy training to give it your best effort. Think about if you were doing 3 times 8 for 2 months, 3 months, 4 months. Your effort would just decrease. You would get bored of resistance training. Even a dedicated lifter would get bored of just doing 3 times 8. So the effort might not have been there if you're just in a really limited rep range with little variation. So I think the resistance training data have limited applicability to dedicated lifters. The training frequency doesn't represent what a dedicated lifter does. If you train more frequently, you have more potential to stimulate growth. There's insufficient volume for all major muscle groups. If you have more high quality volume, growth is going to be stimulated to the highest level in all muscles. Next, the protocols don't mimic what lifters do in reality with the exercise selection, the manipulation of the variables, the sets, the rest intervals, the auto regulation, the drop sets, sort of those advanced lifting techniques that we know can be beneficial, they're just not there. And the scariest one is obviously the effort. Hopefully the participants gave it their effort and they didn't get bored doing 3 times 8 for 3 weeks or 3 months. So ultimately, here's what it comes down to. Somewhere on your body needs repair when you're always training. So somewhere on your body needs amino acids, needs more protein if you're always lifting, if you're training more frequently, 4, 5, 6, 7 days a week. And then growth is stimulated in more areas. So more total area needs amino acids, your calves, your forearms, your rear delts. You're creating a need for protein in those specific muscles that you hit. And obviously, if you don't hit them, you just don't need that protein. And then you're overloading with auto regulation and variety to better manage damage. We didn't talk about muscle damage, but your muscles grow better when damage is lower. The protein you consume is more than likely going to go towards the growth and synthesis of new mass rather than the repair of existing mass. So we didn't exactly have that element of auto regulation and using multiple angles to strategically manage damage and potentially grow more muscle. If we're just doing rows all day on our back, even if the volume is relatively low, we might just blow that one angle out and create damage in that particular area of the back if that's all we're hitting. So ultimately, if you have these 3 factors, if you train more often, train more area, and if you strategically kind of go at your training to better manage damage, you can likely handle more protein. You can have that double meat at Chipotle and make use of it. So you got to think about, does this conclusion apply to me or my clients? Protein intakes at amounts greater than 1.6 gram per kilogram per day do not further contribute to resistance training induced gains in fat-free mass. Well, maybe if you're training 3 times a week and only 3 to 4 sets per major muscle group, and you might not be stimulating all of your body, maybe that's your conclusion. But if you're a little different, if you're a dedicated lifter doing more, creating a need for more protein, this might not apply to you, and you got to interpret that conclusion, and that's your decision. It's on you. So okay, now we're going to move on to the next study. We're going to look at some data and some serious lifters. Oh, this CrossFit. My bad. Okay, here we go. Serious lifters. Here we go. The meathead, This is a serious lifter. It's also known as bodybuilders. So now we're going to look at data in bodybuilders. And lesson 2 is healthy skepticism. Indicator amino acid derived estimate of dietary protein requirements for male bodybuilders on a non-training day is several fold greater than the current recommended dietary allowance. So this study was pretty similar to the last study, and they wanted to find a protein intake that was sufficient for bodybuilders. So what's kind of that high end? And they had a similar conclusion of 1.7. They used the confidence interval to 2.2 grams per kilogram per day of protein. So it's a relatively similar intake compared to the last study. So here's the study rationale. This is a mouthful. Presumably, the protein requirements for bodybuilders who are attempting to build or maintain a much greater than typical fat-free mass would be more related to the minimum intake necessary to maximize whole body protein synthesis, anabolism, for the repair and remodeling processes necessary to induce maximal muscle growth, hypertrophy. In English, do bodybuilders need more protein to build and maintain their mass because they're larger and they're always training? I thought this study design was a little bit interesting. They used a greater than 48-hour rest period prior to data collection, and this is going to minimize the influence of muscle protein synthesis. But it's as if you want to study nutrient needs for growth, repair, and remodeling processes, but minimize the impact of training. You want to minimize what makes bodybuilders so unique. So I just thought that was puzzling. You want to look at how much protein do you need to build, but you're going to minimize the stimulus that triggers the growth. So that's a little puzzling. But anyways, we're just going to see, did the researchers use bodybuilders? That was their definition. So did they truly use bodybuilders? So here are the criteria. They were healthy men between the ages of 18 and 40 years old, strength training greater than 3 years, greater than 4 days a week for an hour a day, stable body mass, non-smoker, intake of alcohol less than 8 grams per day. My research is in alcohol, and this just made me kind of raise an eyebrow. I wanted more detail. So is this a total maximum intake per day? Because that would essentially mean abstaining. Less than 8 grams, this is about half of a drink, half of beer, half a shot. In practicality, nobody's going to crack a beer and drink half of it or do half a shot. So this is such a low amount of alcohol that this would essentially mean abstaining from alcohol. Because in practicality, you just don't drink that little per day. So if they were abstaining, why wouldn't you just say they were abstaining? To me, this alcohol intake sort of opens the door, and maybe it's an average per day, and this means drinking is possible. So let's look at kind of what this would translate to if this is an average per day. We have 7 days in a week, so here's 7. The limit's kind of 8 grams a day, so 8 times 7 is 56 grams of alcohol per week. If we divide that by 14 grams per drink, 56 divided by 14, this opens the door for 4 drinks a week. 4 drinks is kind of right where binge drinking starts. Now, I don't know about you guys, but back in the day when I was binge drinking, I mean, after that 4th drink, I was just trying to catch vibes with a sweet set of blue eyes. I wasn't necessarily concerned about my 5th drink or my 6th drink or my 7th drink. So what this does potentially, if you're going to say you can have 4 drinks, in practicality, who stops at 4 drinks? Once you're 4 beers in, who cares about the 5th? So this is just potentially dangerous, and then it can open the door for binge drinking. If you're talking about potentially allowing weekly binge drinking, you're not talking about bodybuilders at that point. That's a totally different population, because a bodybuilder, they're just a serious one, they're just not going to binge drink once a week. So your population kind of raises an eyebrow. It makes me question, is this truly bodybuilders right here? Then, of course, how long? Is this before the study? Is this like a month before the study, a year before the study? Is this during the study? So I just have more questions on the alcohol measurement. And it's a really influential behavior that can make me kind of analyze and think about who we're actually looking at. Next, it's a non-medication user, so no anabolic steroids and without allergies to milk or milk products. So here's who they got. Here are the bodybuilders. They're 185 pounds, they're 5'7", 13% body fat, and 22.5 years old. this is going to translate to 2.76 pounds per inch. So I'm a little taller. I had to sort of contextualize this. If you're 6 foot and you have 2.76 pounds per inch, you're 198 pounds. Greater than strength training for 3 years, 6 foot, 198 pounds. I think if you're training for that long, a bodybuilder would be a little bit bigger. 6 foot, 198, to me, that's kind of like a swimmer or maybe a high schooler who just discovered creatine his senior year. That's not necessarily a dedicated bodybuilder who's doing the little things, the details to grow more muscle. So these might not be bodybuilders. So I found another study that looked at body composition in Division I running backs just so we can compare. I chose the running back position. A running back is someone who doesn't necessarily strive for a great amount of mass. It's not a tight end, it's not a lineman, it's not a linebacker. Their training goals are primarily power and strength, and hypertrophy is like a tertiary effect. So these Division I running backs were 208 pounds, 5'10", 14% body fat, and much younger. And they were relatively bigger. They had more muscle. They're 2.97 pounds per inch. Remember, similar body fat. So these running backs who were much younger were bigger, and their goal isn't necessarily to maximize muscle growth like a bodybuilder. Now, I know what you're thinking. A D1 running back, this is a genetic freak. This is a unit. This is a monster. D1 players are scary. They're huge. So if you look at the authors of this study, they're from the University of North Carolina. I'm going to guess that they analyzed the football players at the University of North Carolina because I'm pretty sure another university is not going to give researchers access to their football team. So again, I think the researchers studied players at the University of North Carolina. They studied UNC football team. UNC football is not exactly a powerhouse, okay? This is a basketball school. I don't see Nick Chubb, Todd Gurley, Derrick Henry, Sony Michel, Dalvin Cook, Cam Akers. They're not coming out of UNC. So in terms of having genetic units, you know, these freaks that, okay, even though they're younger, you know, they're likely going to have more muscle. I don't think they're going to be at the University of North Carolina because this is primarily a basketball school. And if you look in 2013, this paper's from 2014, so they likely did the 2013 roster. They had nobody from the NFL draft. They were the third to worst team in their division of the ACC. So it's just not a powerhouse. There's no, you know, real monsters that would kind of distort these numbers to make the running backs way bigger than the bodybuilders. So ultimately, I think the bodybuilders weren't really bodybuilders. I think they were recreational lifters labeled as bodybuilders. Now, if you're not convinced comparing them to running backs, I have this other tidbit that was really interesting. They did the criteria. And then at the very bottom of the paragraph describing the participants, they had this little last sentence that was extremely interesting. All of the participants engaged in strength training, primarily with minimal aerobic activity, 20 minutes per week walking in their training routine. Let's dive into this sentence more. 20 minutes a week. So if you did more than 20 minutes a week of cardio, you're essentially disqualified. So this is basically exclusion criteria. So think about if you're training 5 times a week and you did a 5-minute warm-up, which all dedicated lifters do a warm-up, 5 times a week, 5-minute warm-up, you've essentially disqualified yourself because that is more cardio than what they're allowing in their training routine. So these lifters really probably couldn't warm up properly. Again, it makes you question the population. Next, dedicated lifters, bodybuilders versus recreational athletes. One of the biggest differences between these two is the element of cardio. Bodybuilders keep the cardio. And I'm not necessarily concerned about the cardio. It's not the cardio. It's doing more than the minimum. It's the principle of the attention to detail. And this is going to translate to all aspects. If you're doing the cardio, if you're doing more than the minimum, I know you're going to hit calves. I know you're going to hit forearms. I know you're going to do the things that are going to create the need for more protein. It's the attention to detail while training that creates the need to support the repair and remodeling processes necessary to induce maximal muscle growth. I don't think they used a population that were doing the details to induce this maximal muscle growth. So if we just kind of take a step back and look at everything, we had the alcohol measurement, which kind of raises eyebrows, makes you ask some questions. We had the no cardio, potentially really limited warm up. The attention to details questionable. You might not have bodybuilders, you might have recreational lifters, in particular the potato chip. This is the population who might binge drink. They're part of the anti-cardio club, and the details are often overlooked. So have a healthy skepticism. The author said bodybuilders, but you be the judge based on their behaviors and what you can potentially infer with the lack of detail, doing the minimum, were these bodybuilders. You have to decide that, and that's how you interpret the conclusion to the study. Lesson 3, we got bias in research. Time-restricted feeding plus resistance training in active females. So time-restricted feeding, this is intermittent fasting. Maybe some of the authors on this paper like to do intermittent fasting. Let's keep that in mind. So what does the abstract say? We had time-restricted feeding. All calories consumed were, looks like an 8-hour feeding window. So it was 16 hours of time-restricted feeding, 8 hours to consume this food. They had a continuous diet group. This was the control. They ate regularly from breakfast until the end of the day. All groups completed this 8-week supervised resistance training and consumed whey protein. Okay, so it looks like we got a couple groups. We have a controlled diet, we have a time-restricted feeding, and then a time-restricted feeding plus HMB. And they did resistance training over 8 weeks. And then we see what happened after 8 weeks. Before we kind of move on, they sort of jumped around in their definition of the population that they were using. They use active populations here. They use active population in the title. And then they said resistance trained females in the methods. So right there, you're kind of asking some questions. What population am I looking at? Are they walking around a lot? Are they having near-death experiences under the squat rack? Because physiologically, these are two totally different populations. And here's what they found out. After looking at these 3 groups and after doing 8 weeks of resistance training, we had comparable fat-free mass accretion, 2 to 3% relative from baseline in all groups. So all the groups gained muscle. Additionally, there was differential effects on fat mass in the control diet. The control diet gained fat. The time-restricted feeding and the time-restricted feeding with HMB lost body fat. So they had similar fat-free mass accretion, skeletal muscle hypertrophy, and performance, but they had this difference in fat mass based on the nutrient timing. So this is really a nutrient timing conclusion. I want you to keep that in the back of your mind. So here are the methods. We had 3 groups: controlled diet, time-restricted feeding plus HMB. We had our 8-week resistance training going on in the middle, and then we did the final assessments. So let's look at the resistance training. First of all, let's look at the participants, because we have to define it. They said active population, then they said trained. So what exactly were the participants that we were looking at? We had healthy female participants aged between 18 and 30 years, who were recruited via posters, emails, and word of mouth. Participants were required to have prior resistance training experience, defined as reporting greater or equal to 1 year of resistance training and a frequency of 2 to 4 sessions per week, with weekly training of major upper and lower body muscle groups. So these were trained females. They were resistance trained. They were doing resistance training. They were lifting for greater than 1 year. And they're doing 2 to 4 sessions in that time period. So here's the protocol that they employed. I want you guys to kind of glance over this. We see some dumbbell rows, dumbbell bench press, barbell shoulder press, dumbbell fly, preacher curls, triceps extensions. We see some of the basic movements that we'd expect to see. They did training 3 times per week, and they did this alternating pattern of a lower body A day, an upper body A, a lower body A, then an upper body B, and then a lower body B. Now they train 3 times per week. So let's do an example. An upper body A, let's say this took place on a Monday. Wednesday, they would do a lower body A. Friday, they would do an upper body B. The next Monday, a lower body B. And then next Wednesday, perhaps another upper body B. So because of this alternating pattern where it's upper, lower, there were weeks where you would only train upper body once a week, about half the study. In the other half of the study, you would only train lower body once a week. So think about that volume. So for you, in your lifting, is this, if you did this for 1 week, is this an overload or a deload? If you just did dumbbell bent over rows, dumbbell bench press, barbell shoulder press, are you going to grow significant amount of muscle? Or are you kind of going to give your body a break? I mean, if the only back workout you're doing is bent over dumbbell rows at 4 sets, is that sort of a deload comparable to what you're doing now? Or is that a significant overload that's going to trigger additional hypertrophy? Now, remember, everyone in this study gained muscle. We had comparable fat-free mass accretion of 2 to 3% from baseline. So in this 8 weeks, this protocol produced significant hypertrophy. I think for most lifters, this would look like a deload week. And if you did this for 8 weeks, this would likely lead to atrophy. I know for a fact if I did this, I would lose my upper chest, my back, my traps, my forearms, my calves, my glutes, my lateral delts, rear delts, obliques, abs, biceps, and triceps. I know I would lose muscle. I mean, if the only back workout I'm doing is a dumbbell row at 4 sets, maybe 5 sets, I'm going to atrophy. My back's going to atrophy. And remember, there were some weeks where you only did 4 sets instead of hit a muscle group twice. So think about your lateral delts and rear delts. We'll do shoulder press right now. If you're doing barbell shoulder press and dumbbell shoulder press, and that's all you're doing, are your lateral delts going to grow? Your rear delts going to grow? Probably not. If the only bicep exercise you're doing in 1 week is 4 sets of preacher curls, you're going to atrophy. And additionally, there's a lot of muscles that really aren't trained as well. Talk about the forearms, talk about the abs, the obliques. You just don't get sufficient overloading volume. And I think for an experienced lifter, this is going to produce significant atrophy after 8 weeks. But remember, all these participants grew muscle, which tells me that if they're recreationally trained lifters, there's certainly a spectrum, and they are way more sold towards the beginner or novice end of the spectrum rather than an advanced lifter. So they're relatively untrained. They're a recreational lifter that's sort of a novice lifter, yet they were described as resistance trained. One more thing. The protein consumption in all groups increased from habitual intakes of 1.1 to 1.2 grams per kilogram per day, as estimated during the pre-intervention period, to an intake of 1.6 grams per kilogram per day in all groups. So let's think about this and relate back to the conclusion where everyone grew muscle. Were these dedicated lifters? Would a dedicated lifter perform that protocol for 8 weeks? Would they sacrifice the complexity of their routine to train 3 days per week in that manner? Then would they make significant gains doing that? Would they gain 2 to 3% muscle doing that? I think the answer is no. So these were not dedicated lifters. They were really untrained novice lifters at best. So if you increase protein by 33 to 45%, we know quantity is way more important than timing, especially in novice lifters. So here's what they did. They added resistance training and they added protein. They added 2 very influential stimulus to produce changes, and they made a nutrient timing conclusion. Okay, we know resistance training is going to drown out any of the effects. We know increasing protein is going to drown out any nutrient timing effects in a novice lifter. You just can't make this conclusion based on what they did, especially if they're using resistance trained females as they describe, which they really weren't resistance trained. And in general, it's not just this study, it's all performance and physique and body composition type research. Can you make conclusions about the details when a foundation is not established? And I think the answer is no. And we see that so often. You're going to introduce variables A and B, and variables A and B are going to dictate the outcome way more than what you're investigating, which is, variable C. Is sort of an after effect. And I think research tends to set up studies in a way that is going to produce a particular conclusion. And it's really hard to generalize the applicability of that conclusion, especially if you're going to investigate these nitty-gritty details in someone who doesn't have the foundation. You can't make a nutrient timing conclusion in someone who's not habitually eating protein and not lifting. There's just other factors that are going to drown the nutrient timing out. So also, let's not forget about the fat loss difference, because this is really important as well. So we spent a lot of time talking about the muscle. Let's talk about the fat loss. So remember, this is essentially a nutrition-based study. They looked at HMB, but obviously the larger conclusions exist with the intermittent fasting. It is worth emphasizing that the dietary advice provided in the present investigation was minimal. Specifically, each participant met briefly, less than 10 minutes, to discuss the assigned eating schedule and protein consumption target with the primary investigator at the time of group assignment. So at the beginning of the study, we spent maybe 5 minutes with these people telling them what they had to do. That's a little concerning considering it's a nutrient timing conclusion. The participants really didn't have much instruction on what they were supposed to be doing from a nutrient timing standpoint. Additionally, let's look at the results. Due to the relative likelihood of behavioral modification or underreporting on diet tracking days, it is possible that both the energy and macronutrient content of the diet actually consumed by participants in all groups was higher than the estimates obtained from weighed diet records. So the accuracy of the diet is questionable. So let's look at the accuracy, what was actually reported. The continual group ate 1,681 calories a day. The intermittent fasting group ate 1,554 calories a day. The intermittent fasting plus HMB ate 1,442 calories per day. Now remember, this data might not be reported right. And if one group is going to report more calories, higher calories, it's likely the group that's going to be, if one group is likely to underreport calories, it's likely the group that is going to be eating more throughout the day. It's the continual eating group. So if any group ate more, it's the continual eating group. But even let's say in a perfect world, these were accurate, even though the researchers say, yeah, they might not have been accurate. The food was not significantly different, therefore it wasn't reported in the abstract, but we know what happens to body composition if there's 130 to 240 calorie difference over the course of 8 weeks. So the fat mass results weren't readily explained because the calorie difference wasn't statistically significant. But if you kind of dive into the results, you could see that there's a huge difference in dietary consumption average per day. And then additionally, let's keep in mind the group that was eating continuously, they had just more opportunity to eat. So they might have ate more and not reported it as well. So these differences in dietary intake might be even larger. So the element of statistical significance, because this diet wasn't, or because the calorie intakes weren't different statistically, it really got overlooked, but it's just sort of a common sense thing. We know if you eat less, you're gonna potentially lose fat. And that's exactly what happened. It really had to deal with the calorie intake rather than the nutrient timing. So let's just branch off real quick now that we're talking about statistical significance. So some findings may or may not be reported in the abstract pending their significance. You guys read research, you're familiar with this. But you need to always consider practicality. So let's do an example. These numbers right here, if we looked at them, they probably don't differ statistically. However, these numbers have a huge meaning. This guy right here is 9.81. He's Usain Bolt. I'm sure you know his name. These guys right here, you don't know their name. And even if you go to the Olympic page, people 5 and 6, they don't even have their picture, they have their country's flag. So even though these numbers might not be statistically different if we ran the stats, they have a huge practical meaning behind them. So just because a number is not significant, whether it be the calorie intake or these 100-meter dash times, always consider the practicality, and the p-value is important, but it has limitations. Lesson 4, we're going to factor in some physiology and kind of relate this back to the studies we analyzed. Let's start with this first study. Spacing wasn't assessed. This is really, really critical because we know when we consume protein, it doesn't matter how much protein we consume, whether it's 50 grams or 25 grams, or the source of protein we eat, whether it's whey, plant protein, or casein, we have a limited capacity to grow. We're going to consume this protein. We're going to increase muscle protein synthesis. We're going to start linking amino acids together, but we have a limited capacity to build. We can only link those amino acids together for so long before growth is reduced. It's extremely important to consume protein throughout the day in order to keep increasing muscle protein synthesis. You just are only capable of so much growing based on one meal. And how you use protein is going to be totally different if you properly spaced it and, 200 grams in 5 meals versus 200 grams in 1 or 2 meals. And protein spacing wasn't assessed. So this is a huge factor to determine how much protein you're going to use. Next, we're looking at why protein synthesis decreases. So we just touched on you have a limited capacity to build based on one meal. So let's kind of look at why that is. Here's baseline times 0. Hopefully you guys can see my mouse. After 90 minutes after you consume protein, you're going to have an increase in muscle protein synthesis, but after 180 minutes, it's going to return back down to baseline unless you have an energy source readily available. Here we have carbs and leucine. These can be oxidized to provide energy to support growth. You can provide ATP to continually linking those amino acids together. Therefore, you can use more protein. Was energy intake assessed in the meta-analysis that looked at 2.2 grams per day as the maximum amount of protein? And it really wasn't. They said participants should not be energy restricting, but think of the population. These are untrained participants. Do they know how much energy they need to eat to support resistance training plus growth? Probably not. So what are the 2 biggest elements that dictate how much protein you can use? Because remember, they had a cap. They said a maximum 1.6 to 2.2 grams per kilogram per day. That's the most you can use. Well, let's look at the 2 biggest elements that determine how much you can use. It's your protein bolus per meal, and it's your energy availability to link those amino acids together. And these were not assessed. So it's hard to make that conclusion if you're not looking at probably the 2 biggest elements that are going to be the rate limiting factors and how much of those amino acids you can truly use for muscle growth purposes. Next, let's look at the intermittent fasting study and let's apply data from pre-sleep research. We know if you consume protein before bed, you can increase muscle protein synthesis. You have more potential to build. If you don't consume protein, it's going to be much harder to build muscle. And there's only a few populations that can potentially build when your meal timing is not exactly optimal. And one of the populations that can is the untrained participant. So exercise-induced increases in muscle protein synthesis are short-lived and peak earlier in the trained state than in the untrained state, resulting in a smaller overall protein synthesis synthetic response in the trained state. So there's physiological differences between trained and untrained participants, which make essentially the anabolic window in the trained state is really short. What this data is getting at is if you're trained, you're going to do resistance training and you're only going to increase protein synthesis for a really relatively small period of time. However, if you're untrained, you don't have this anabolic window. You have this huge window to feed. It's like an anabolic 6-car garage, and you have a massive capacity to build throughout the day. Protein synthesis is increased way more, and therefore the timing of those meals, it really doesn't matter as much, which washes out that intermittent fasting conclusion. Now, let's relate this back to the first study again. So wouldn't untrained people grow more? Because remember, we had all these untrained participants and the maximum protein intake, and now you're telling us they have likely more potential to grow. Remember, resistance training is just the signal to grow. You still need the raw materials to grow. The intermittent fasting study, we know participants were hypercaloric in the 8 hours. We know they had a lot of amino acids. We know they were jamming calories into that 8 hours so they could take advantage of the protein synthesis response post-workout. Remember, it's a huge, huge window to grow. Energy wasn't assessed for the protein recommendation meta-analysis, so we just don't know if they were hypercaloric. The rate limiting growth factor wasn't thoroughly examined. So even though these participants were untrained, we don't know if they had the energy to support that growth. So even if they had the signal to stimulate growth, you always need the raw materials. The signal created from resistance training simply isn't enough. So ultimately, what you have here, when you tie back the physiology, is you're tying back everything you learn in your courses. So you're going to study all these pathways, and they're not going to make sense at first, and they're going to be really frustrating, and they're really annoying, and you're wondering why you have to do this. Essentially, I mean, I'm a little bit older in terms of the PhD thing, but the best advice I could give would just be to become a unit. Know it all from the basic science to the applied science. This is going to make you a better researcher, a better reader of research, and most importantly, a better practitioner in whatever you do and move on to. If you know it all, from the basic science to the applied science, you can sort of manipulate the cell physiology, and then you can really get the desired result you want, or you can interpret data and think, does that make sense? And from there, you can look at the generalizability of studies and the applicability of studies to your specific population of interest. So here are closing thoughts. Who here works out? It's not this doesn't hit the same on Zoom, but it's not a trick question. Hopefully we got some Zoom people. We got Dr. Ormsby raising his little Zoom hand. So if you ever work out, there's different levels to it. There's going through the motions. There's going through the motions of a workout versus being into a workout. And you're kind of staring at the weight, you're just kind of moving it, versus if you're hyped up and you're into it, so you're going to get a different result. You're going to get a totally different experience. You're going to have a better quality product at the end of your workout. And the same thing happens when you read a paper. You get a totally different experience depending how into the paper you are. You can go through the motions of the paper, or you can really get into the paper. And if you get into the paper, you're going to get more out of it. And that's going to be highly advantageous to whatever it is you do, or whatever conclusions you try to generalize from that study. Next, you got to think while you read. So does the population apply to me or the population I'm interested in? So we talked about lifters eating 2.2 grams per kilogram per day. Well, where does that data come from? It's based on novice lifters who aren't really giving high quality volume to stimulate that growth. So that conclusion might not apply to you if you're doing more and if you're a trained lifter. And then what are the methods? Is this something you do in real life? Would you do 1 to 2 sets per major muscle group? What variables were manipulated? Were all the rest intervals 60 seconds? Do you use 60 seconds? Does this only apply to a lab setting? It's also critical. What's the conclusion? Do the results support this? Statistical significance. So what is statistically significant and what is meaningful? What has that magnitude-based inference? And then why and how and the mechanisms and the science. And the science really helps you put everything together and ultimately gives you the ability to generalize the study to a particular group, which is ultimately what you want to do. You want to take something out of study. You don't just want to read it. And then, of course, you got to always remember studies have limitations. What are they? Make note of those limitations, but also understand it's very difficult to write practical methods. When you write these methods, you're not writing them by yourself. You have a team. So you're going to have this guy, he wants to incorporate this interest, and this girl, she wants to incorporate her interest. And then this guy's specialty is there, so you're trying to curve into that. Then at the top rope, one dude, he does online survey work. Next, you're trying to learn who Qualtrics is, and that's really annoying. So there's all these different angles, and you're getting bombarded with all these different things. It's really tricky to write good methods. So what you read that kind of flows really concise, there was 50 shades of edits in that, and it likely had many, many turns to get to where it had to be. So acknowledge the limits, but respect the research. It's really hard to do. especially getting concise methods that everyone on your committee really likes. Then money's often limited, especially if we're dealing with physique and performance research. Researchers also have bias. So nobody likes to be wrong. If you're doing intermittent fasting, you don't want it to show that it led to greater atrophy. Therefore, you might design a study to maybe, I don't want to say manufacture, but sway towards a particular conclusion. And personal profits there. You don't get in research for the cheese. You gotta, if you can find a study that can potentially support one of your theories, and then maybe you could write a book or do some counseling or maybe do a little website off of that, finding that might be influential to influence the results of those research. And then publishing might be easier when you find significant differences. I'm not saying it's guaranteed to be easier when you find significant differences, but if you're going to write an abstract and there's something as opposed to nothing, that might be easier to publish. Now, granted, those null findings, those nothings, those are very important as well. And research just needs to sort of do a better job in highlighting the null findings. That's just my opinion. And then, of course, this is the biggest one. If you start from rock bottom, you essentially have this floor effect, or if you manipulate some variables, you manipulate variable A and variable B, and then you try to investigate variable C, you really can't look at variable C if variables A and B were much larger influential factors. In general, if somebody starts from the bottom, they have a lot of room to grow. So they're going to start low and end up high. So there's a huge room for change. And once again, it's easier to publish if you find those good changes. So the population of interest in research is typically one that has a lot of room to grow. So, okay. Hope you guys kind of took something out of this and you kind of look at research with a little more, healthy skepticism, and you're factoring some science. You don't just interpret exactly what researchers give you. You kind of just stop and pause and think. So if there's any questions, it'd be a good time.
All right, let's give Chester a big round of Zoom applause, everybody. Great job, Chester. Let's go ahead and stop the recording.